All right. Hello, everyone. Good afternoon. Good morning. We hope you all have a nice day. We're glad you could join us for today's presentation. My name is Kayla. I'm here representing the Acelab team, and we have Bob here from ATAS. So before I pass it over to Bob to walk us through the presentation, I want to go over some quick housekeeping items and then just general information. In just a moment, you should be able to see my screen here. I am on Acelab. So if you're not familiar with Acelab, there's the search bar at the top of your screen. That's a great way to search for specific manufacturers. Just make sure you click this manufacturers button. You'll see we also have our new AI search enabled. That's a really great way to ask, specific questions and get some material research going. Um, Anyways, on ATAS's page here, we've got some information. We've got some contact information, as well as video and all of their products here for you to explore. So you can click into any one of these product pages to get more information on anything. You can also save it to your firm library here. That way you have it there for your future reference. But they've got, plenty of products here for you to explore. So I will drop the link to their product page, or sorry, their brand page here in the chat, so that way you guys can all check it out. Few other things to make note of. Um, so today is an AIA approved presentation. We did collect your numbers already upon registration, so you should already be good to go there. If you're worried we didn't get your number, I'll put a form in the chat as well, so that way you can fill that and make sure we get your number and that you get credit. We will also be doing a poll today, so if you've joined us before, you've heard me say this already, but it is an optional poll. So if you're not interested in getting any kind of follow-up emails or anything, just click the X, it'll go away. However, if you are interested in getting in touch with Bob and his team after the webinar, fill out that poll. We will connect to you via email. And you can respond directly to that email to respond to Bob and his team. You can ask specific questions, anything like that. You can also log into your Acelab account and see all of your open conversations there. Um, and we will also be doing Q&A. So just want to make sure that you see that Q&A button at the bottom of your screen. Click that, drop any questions in there throughout the presentation. We'll get to as many as we can at the end. I think that pretty much covers everything on my end. So Bob, I'll go ahead and pass it over to you.
Great, thanks, Kayla. So self-introduction, I don't have it on my screen, it just says Bob. I'm Bob LeClare. I am the Director of Perimeter Edge Business for ATAS International, and that's what we'll be talking about today is a Perimeter Edge metals. To start out, just real quick, an overview for those that don't know ATAS. ATAS stands for Aluminum Trims and Shapes. What we started out doing was aluminum trims and shapes, but we do so much more now. We just go by ATAS. The company was founded in 1963 by Jack Buss, and it's still a family-owned and run business. Third generation is now involved in ATAS. Company started out just doing siding out of the basement in Rochester, New York. Little simple 10-foot shop break, making trim in the evenings and delivering it to contractors during the day. We've grown considerably since then. Have 5 manufacturing locations. Our headquarters in Allentown, Pennsylvania. We have a location in Mesa, Arizona, University Park, Illinois, and a new acquisition I'll talk about in a minute in Elkton, Maryland. We also have our own division called Brightsmith. That's a coil coater as well as a post paint operation. So we do paint our coil sheet and then also post paint materials. So been in business over 60 years, still family run, has that family feel. We do a variety of architectural metal products, single skin wall panels, perforated metal panels, metal roofing, tapered, curved, custom fabrication, column covers, insulated metal panels, interiors, ceilings and soffits, kind of taking what we've been doing on the outside and take that into the inside. Perimeter edge, which is what I'm going to be talking about today. Architectural accents, accessories, secondary framing, framing for both walls and roofs. And as I said, we just acquired a company called Metalworks in Elkton, Maryland, which takes us into plate. Most of our other products have been lighter gauge 063 and lighter sheet metal. Metalworks does architectural metal panels, column covers, heavier gauge, typically 080 and heavier. So a little bit broadening, again, more of the scope of what ATAS does. Our website has a lot of information. Kaylee just kind of touched on that some, but you can go in there and help you write specifications. Submittal builder, you can pull up details of our products, CAD details and BIM models for drawings. There's photos of past projects. It's a lot of good information on there if you want to learn more about ATAS and what we do, not just in Edge Metal, but in all our other products. Okay, so get into the presentation, design and testing of perimeter edge metal for low slope commercial roofs. That lengthy title pretty much says what we're talking about. It's edge metal and for commercial roofing, low slope. As Kayla mentioned, this is an AIA-approved presentation. It is copyrighted, but reach out to me or Kayla or anybody, and if there's something in here that you would like to get a copy of, I'm sure we can take care of you. Find something interesting, I'm happy to share it. Learning objectives. So what we're going to look at is kind of what are our conditions at the perimeter that we're calling perimeter edge metal. What are we talking about? What are those three conditions? We're going to look at the key factors that affect the wind loads on a building and how you can calculate the pressures on your edge metal. Talk about some test standards that are required by code and what those are and how they're done. And then I'm going to wrap up with kind of just talking about some general design characteristics and things you need to consider for metal in general, but more specifically for perimeter edge metal. So I always like to start out with, when I say perimeter edge metal, what are we talking about? What is perimeter edge metal? And I'm going to talk about coping. So when you have a parapet wall, a wall that stands up above the roof, and you put a piece on it, I'm going to call it coping. Some people call it a wall cap flashing, wall coping, whatever you want to call it. But I'm going to go by the term coping. And then typically when you don't have a parapet wall, you're going to have an edge metal, which we'll call a fascia, drip edge, gravel stop is a common term. And I'm going to talk a little bit, that's traditionally been used when there's not a parapet wall, but I'm going to talk a little bit later that I'm seeing more and more cases where you can use a fascia on a parapet wall with a single ply roof membrane. We'll talk about that a little bit later too. And then finally, gutter. And I talk about water control being gutters, downspouts, scuppers, collector boxes. Really in this presentation, because we're talking about perimeter of the roof, I'm going to really just be focusing on the gutter itself. So your perimeter edge metal, it can be an architectural feature on your building. Maybe it's something decorative like these arched entrances. And this isn't even a low slope project, but they really wanted the nice curved coping to give that look. So that's what we did to give a nice architectural feature on the building. Maybe it's you don't even want it to read, you want it to blend in, be inconspicuous. These are some panel jobs where you can see, especially on the right, they wanted that horizontal lines and the edge metal's up there, but it just blends right in with the wall panels. But it does serve a function. It secures a roof. And that's really what we're going to get in today, is not just the aesthetics, and more so than the aesthetics, really the performance of your edge metal and how important that is. Aesthetically, though, I always like to point out that on most low slope roofs, it may be the only part of the roof system you see. So you'd certainly not only want it to function, hold your roof in place, but also to look nice. Like I said, you don't want it to be an eyesore. Nobody wants oil canned or flat or edge metal flapping in the breeze, like in this picture. Don't want it to detract from the building. This is a Red Robin gourmet burger chain, and they have these arches on either side of the entrance. And really, from a half-mile away driving down the street, you can recognize one of these buildings. And that was their signature part of the building, was to have a nice, smooth arched and a radius at the top. And somebody value engineered it and said, we can just do this. And it's certainly not the look they wanted. And other than this being segmented, not looking good on the arch here, you can see at the top, it's coming loose. So it's not only looks bad, it's really not performing like it needs to. You don't want your coping blowing off, your gravel stop blowing loose like this. And when these blow off, this picture on the left is coping, they don't just fall off like that. That's tumbled across the roof. Somebody's just tried to clean up and brought it back to the edge, but lost a lot of metal there. It's certainly not what you want. Fortunately, on that picture on the left, you didn't lose the roofing, but quite commonly when your edge metal fails, you do lose your roof. So kind of continuing on that, why perimeter edge metal is important. There's a group called RCAWI, it's Roofing Industry Committee on Weather Issues. When they first started, they only studied wind. That W was for wind, but now study hail, and they're actually starting to look into wildfires too. So they're looking at weather issues that affect roofing. Or they go out mostly and do investigations after hail or wind events and just document what happened, trying to figure out where they're seeing failures and possibly what caused those failures. They write some really good reports and put those out. And if you're interested, they're free to review and download at Evercowie's website. They got out and investigated after many different hurricanes. And what they found is that failure of the roof system was typically because the perimeter edge metal failed. The roofs don't just fail out in the center. The membrane attachment can be good in the center, but when the edge fails, it goes into peel and they lose the roof membrane. They've done many investigations, and although over time, as we've gotten better at making better roof edge, it's still when the roofs are failing, that's where the failing is at the edge. This picture is from one of their investigations. I just talk quickly about this picture. I don't think that using a ballasted roof in a high wind area was a good design, especially without a parapet. But you can see what happened here is what's we assume nobody was up on the roof watching it, is that ballast got scrubbed back, and when it did, the membrane bellowed up, and it was just pulling on that edge, and it pulled loose the edge metal and in some places the wood blocking. Well, again, now your roof goes into peel and your membrane's gone, your insulation's exposed, some of that's gotten blown loose, and we're actually starting to lose decking here. So you've got what's getting to be almost a structural failure, and certainly allowing a lot of water infiltration just because the edge metal didn't hold. They found that in the investigations that nearly 95% of roof failures were caused by poor workmanship and substituted materials, which to me means I think as an industry, we know how to do this right most of the time. We know what the right products are, but maybe somebody substitutes it, value engineers use something that wasn't what was designed, or they just didn't know how to install it properly or for some other reason didn't install it properly and it causes it to fail. Materials are just frequently not, when it fails, typically not tested or not using the right gauge. So like in this picture, you have a fascia and that piece hanging over the edge would be your cleat. It's too light a gauge and it obviously didn't hold. Maybe it wasn't fastened well either, but it came loose. And I'm aware on this roof, it failed a lot more than you see here. This is kind of where the failure stopped. If you go up higher in this picture in the corner, they've lost their whole roof because that edge metal failed. It was Hurricane Andrew was a major hurricane that went through South Florida in 1992. It's been quite a while ago, but it was as opposed to Katrina, which was a major event because of flooding. Andrew was really a wind event. A lot of damage due to high winds, and it was estimated that 75% of the losses, we're talking about insurance claims from that storm, were due to roof failure. So that's why it became so important. We said we got to get this right. And insurance companies like, well, we're paying out all this money because the roof failed. There's been, like I said, Recovery reported the edge metal failure as a common cause of roof failure. FM Global Insurance Company investigated a bunch of claims that they had for doing a study of built-up roofs, and they found that 59% of the roof failures were because the edge metal failed. So it shows again how critical this is to getting your roof to perform. Hurricane Andrew was estimated of $26 billion of damage back in that time. You could probably double that number today, but 26 billion in damages. And if 75% was due to roofing, you're talking like 20 billion in damages just from roofing. And then I think, well, if 60% of that's because the edge metal failure, now you're talking like $11 billion in damage from that one storm just because the edge metal failed. So it shows how important getting the edge metal right is. I'm sure there's a lot of people on this call that are not in hurricane zones. You get high winds everywhere. You don't have to be in a hurricane. They may not be as high winds, but you still get high winds that can do damage. This is a roof that blew off in Muscatine, Iowa. It's in Iowa, right along the Mississippi River. And it was straight line winds that blew us off, probably a microburst or a downburst, big thunderstorm. Was not a tornado. It's another picture, and this roof didn't actually fail, but those ballast pavers around the perimeter are designed to hold down the roof. And I just think this is an interesting picture because it shows how much wind force you have to cause those ballast pavers to flip up. Those are about 8 inches by 16 inches, about an inch thick concrete. This was in Birmingham, Alabama. Not Certainly not a hurricane. Alabama's in coastal and it wasn't a hurricane. 110-mile-an-hour winds, and we know exactly it was that speed because there was a anemometer, a wind speed indicator on this building, and clocked them at 110. This is kind of a high wind. You're playing microburst. 110 is very high wind speeds, probably right about a maximum code event. And this wind came across this open field, so you had not much breaking it up. Hit right in the corner of the building, which is the most vulnerable part. And that pattern we see where these pavers are flipped up, kind of again, that V pattern is really common. That's what the wind does when it hits that corner. It spins off in a vortex, a V pattern like that, and flipped up those pavers. That shows exactly what the wind forces do. And you can see most of the damage is in the corner, the most vulnerable part. Um, Interesting fact, that V pattern, that's why geese fly in a V, because the geese on the back part of the V, they're getting uplift from the geese in front of them. So they're not having to work as hard if you're at the back of that V. The goose out in the front's doing the majority of the work. I'm going to talk about this picture again a little bit later, but just again shows the wind forces. Not really a roof failure there, but showing what kind of winds you can get. This is not a high wind, but it's a very good illustration of what wind does when it hits a building. This is a fog rolling at an extremely low speed, probably just a mile or two an hour, and hitting these buildings. And what happens when wind comes in this case, it'd be coming from right to left, coming off the coast, hits the building, you're going to get some downdraft. Some of that wind's going to go down the building, some of it's going to go around the side, but the majority of that wind's going to go up the face of the building, and right at the very top of that building, you get separation, and that creates negative uplift. This is what it looks like graphically. The blue lines will be the wind flow coming in, and those red arrows, those vectors, are indicating the negative uplift. It's really a suction trying to lift that roof up. And the longer the arrow, the greater the uplift, the greater the negative pressure. So you can see here that the greatest is right at the edge of the building, the perimeter, which is where we're talking about our perimeter edge metal. As it gets out of the field of the roof, it reattaches and you don't have nearly as much uplift until you get to the other side of the building, and you're going to get negative pressure on that side. It's just graphically showing the wind forces on coping and on fascia. The top picture on the left is the airflow going across the coping. That kind of swirling pattern at the top is indicating that negative pressure trying to pull up. And then on the right for the coping, it shows those vectors showing that the force is pulling out on the face and the top and the back. It doesn't do all three of those at the same time, but it will do two of them at the same time, either top and back or top and face. Then the lower is just showing for a fascia that those forces, you get the same thing, but really predominantly you're looking at a negative pressure pulling out on the face of a fascia or gravel stop. This is important because you'll see later when I talk about how we're testing edge metal, these are the loads we're trying to simulate when we're doing testing. It's just a little bit about how you design for a roof for these negative pressures. This would be another hour-long class. We're not going to talk about roof design right now, but when you go, there's a document called ASCE7, American Society of Civil Engineers document that tells you how to figure all the loads on your building, and it's on the roof and the walls. And here it's showing a roof plan, and that zone 1 is in the center of the roof, the field of the roof, and that has the lowest amount of uplift pressure. It's going to get higher in zone 2 at the perimeter, and then the very highest is in zone 3. And so again, here we're talking about edge metal is in zone 2s and 3s. It's where your greatest uplift pressure is, and that's what we're trying to design for perimeter edge metal. And back to this picture, it's kind of interesting to show that this designer knew that. Zone 3, the highest uplift, the pressure, they put the ballast pavers because they traditionally perform better than stone ballast. And they kept that in the perimeter in zone 2. And then they put stone ballast in the field of the roof in zone 1. And as you can see, I think it was a good design. This stone ballast didn't move much at all. A little bit here, this one spot, but I'm pretty certain that happened after the ballast pavers flipped up. So they had it right. I said earlier, poor workmanship and substituted materials are common cause of failures. I'm going to assume that this was the right material, being a ballast paver and the stone ballast. But there was a poor workmanship error here, and I think the installer probably just didn't know that those ballast pavers should not have been stacked joints like they're shown there, but they should have been staggered joints, like a running bond if you're doing masonry. And if they'd done those right, they all lock together. They're tongue and groove on the edges, and I don't think this would have failed. This was, again, said was not a roof failure. The membrane that's flipped up there, that was just a protective mat. So they were able to relay those down and get this roof to perform once they got it installed right. I'm going to talk about three standards: ANSI SPRY ES1, ANSI SPRY FM4435 ES1, and then ANSI SPRY GT1. All three of these standards have that ANSI and SPRY in the name. SPRY is a single-ply roofing industry. It's a trade association of manufacturers of roof membranes and those that provide raw materials or accessories for that industry. So ATAS is involved in SPRY because we make perimeter edge metal. SPRY started out as really a marketing group, just trying to promote the idea of single-ply roofing when that first came into the industry. When single-ply was new. Before that, it was all built up or maybe modified. So single-ply was a new idea, but SPRY is really involved more now into a technical organization. Single-ply is by far the vast majority of roofing now, and so they're really just trying to create better roofs, make sure it's done right, educate, and write standards and do code development. So SPRY's developed a number of standards, including those three I just mentioned. They do not just develop those standards in a vacuum. When they create the standards, they send them out to the industry and canvases, and anybody in the industry that wants to can make comments on it. And if they disagree with the standard, you go back and forth until you to get a consensus-based standard. And that's what ANSI does. The American National Standards Institute just oversees the standard development to make sure that when you're done with the standard, it's consensus-based and everybody in the industry says, okay, this isn't just what SPRY thinks, we all agree with it. So the first standard, this ANSI SPRY ES1, was the first wind design standard for edge systems used with low slope roofing. It's been out since 1999, I believe, and it was first included in code, International Building Code, in 2003. So the requirement for this testing, a code requirement, has been around for a long time, since 2003. It's still not being strictly enforced or probably followed as much as it should be, but it is a code requirement that on all commercial building, low slope buildings, you should be using tested edge metal. When the standard, when this code first was shown, it said that it should be designed in accordance with ES1. They revised that in 2006, and this was a good revision, saying that really the design should be according to Chapter 16 in code, which tells you how to calculate those wind loads using ASC 7 that I was just talking about, but that you should be testing for ES1. No change in 2009. 2012, they just kind of changed the language just to clarify that we're talking about built up, modified, and single ply roofs, which I think would be pretty much almost all your low slope roofs, except maybe spray foam or maybe a metal roof. But even then, I don't think it'd be a bad idea to have your edge metal tested, because even if it does not secure the roof, you still don't want edge metal blowing around. All these you'll see also say except gutters. So at this time, we're talking about testing just copings and fascias. And it says also your edge securement for, it's kind of, I want to talk about this, edge securement for low slope roofs. So it's edge securement except gutters. In 2018, they changed it to a newer version of standard, which is ANSI SPRY FM4435 ES1. It's the standard was revised a little bit to make it just a test standard. They tweaked the way it was testing a little bit based on some collaborations SPRY did with Factory Mutual. And then in 2021, just a little bit of code language. And as I said before, it used to say edge securement for low slope roofs. They changed to say edge systems for low slope roofs. And the reason for this, it's a minor wording, but what they wanted to make it clear was whether your edge metal secures your roof or not, it still needs to be tested. Because I think there's some people thinking, oh, if I have a coping that's not securing my roof system, it doesn't have to be tested because it's not an edge securement. And the International Code Council looked at that and said, no, we really don't want 10, 12-foot piece of metal flying through the air, cutting up roofs, breaking windows, doing damage, possibly bodily harm during a high wind event. So we want all our edge metal tested. So that's what was in 2021. So like I said, in 2006 and later versions of code state that it should be designed per Chapter 16, not through ES1, but by Chapter 16, which is again based on ASCE 7. It's going to go through that real quick to get everybody an idea of what are the factors that impact the loads on your building, and then to run an example to give you an idea what the magnitude of these wind loads are. There are four primary factors you need to think about when designing your wind loads for your buildings. What's the wind speed where your building's going to be located? what's the building height, the building exposure, what's around it, and then an importance factor, what your building is used for. So start with a wind speed. There's wind speed maps. You can look these up in ASE7. There's different versions of ASE7. The maps change a little bit, but not drastically. The calculations all still work out about the same. So this is an example of a map from ASE7 in 2010. You can see the higher winds at the coastal regions, and then again, in center of the country, it's pretty much 120-mile-an-hour winds. A couple little specialty zones that you can see over here in Appalachian Mountains. Where I'm from, there's a gray area. That's because you get some wind tunnel effects going through the mountains. Building height is pretty basic, just from the ground to wherever your roof level is that you're designing for. If you don't want to do every roof level, you can do the highest one and just be conservative and design everything to that one building height. And then the terrain, what's around it. This makes an impact on how that wind, how forceful and how direct that wind is when it hits the building. Exposure B is urban and suburban. This is probably most common what people are designing for. Exposure C is open terrain, so there's some obstructions. It would be like that insurance building with those pavers I showed you, they're flipped up. That would definitely be an exposure C. And then exposure D is seacoast. And seacoast doesn't have to be on the ocean. It's a mile of open water. So if you're designing on the Great Lakes, you could clearly be an exposure D, something like that. For the curious, exposure A used to be urban. They had a separate classification for urban, but they realized it's not really that different than suburban, and so they put them together. And then what's the importance factor? What's this building used for? And this isn't a safety factor. It's just a little bit of a multiplier you put into the calculation. Category 1 would be low hazard to human life. This would be a warehouse. There's probably nobody living in it, never really has many people in it. Category 3, they classify as all others. It's typically 300 or less occupants. And then category 3 is a substantial hazard to human life. That'd be 300 or more occupants. And then finally, category 5 is an essential facility. This would be a hospital, a fire station, police stations, frequently be schools if they're going to be used for shelters or something like that. I like to say prisons. You're not going to be evacuating those in high wind events. So it's buildings you need to make sure withstand aren't going to have any chance of failing during a storm. There's a calculation you can do. Everybody looks at this formula and panics. It's really just multiplying some numbers together. You look at in tables, but I'm not going to spend time doing that. There's some online calculators you can use. And I'm going to show an example using the National Roofing Contractors Association wind calculator. This is a nice calculator for really all parts of your roof design, not just the edge metal, for those who are doing roof designs. roofwinddesigner.nrca.net. So for this example, I'm just going to say we're looking at a 70-foot tall hospital in Chicago, Illinois. You can look at that and know that it's 120-mile wind speed. That calculator will help you determine that if you don't know. Exposure D could run Lake Michigan, and then it's a hospital, so it's a category 4. And if you go to the calculator, you can put in these inputs. You put in your building, your roof size. Not as important for what we're doing here because we're looking at just the perimeter edge. Looking at the roof height, it's a low slope roof, what you might call a flat roof. In this case, I'm going to say no parapet because we're just designing perimeter edge. The parapet will make a difference out on the field of your roof, but it won't for what we're doing here. Exposure D because it's on the Great Lakes, and then it's that risk category 4. You can put in some other factors as far as the deck type and roof membrane, but again, for what we're doing, that's not as important. And with that, then it's going to give you results that look like this. And we're showing the roof and again, we're not worried for perimeter edge about the field of the roof. That's zone 1, but zone 2 is the perimeter. And it shows a negative uplift of 62.8 pounds per square foot in the perimeter. And then that goes to 85.5 pounds at the corner. And the corner, it's a corner region. It's not just like the corner of a fabricated coping. That can extend 10, 20 feet away from the corner, depending on the configuration of the building. And then zone 4 is out on the face at the perimeter at 32 pounds. And zone 5 is out on the face of the corner at 50 pounds. There's no safety factor in that, and it's recommended to use a safety factor of 2.0. So again, this calculator gives you that information. So we're looking at in zone 3 at the perimeter, 171 pounds per square foot pulling out the top of a coping, and in the corner, 100 pounds per square foot pulling out on the face of a coping or the face of a fascia. So, you think about a coping that's 12 inches wide. That's not a very wide wall for a parapet. So 12 inches wide and a 10-foot long piece of coping would be 10 square feet. At 171 pounds per square foot, you're talking 1,711 pounds of force trying to pull that coping off. So it's not just, hey, let's see what works. It's why we're testing it. This is really a pretty big load we're trying to make sure our coping systems resist. In this standard, the ANSI SPY from 4435, there are 3 test methods that we use to test our edge systems, RE1, 2, and 3. RE just stands for roof edge. And this is a diagram, and this goes along. I took out of that calculator also because it's nice. It takes the loads we just calculated and shows them how you would test for it. So RE1 test is testing the ability of fascia gravel stop to restrain a membrane. This test is only required for mechanically attached or ballasted systems that do not have any attachment, any fasteners within 12 inches of the edge. That attachment in the industry, we typically call it a peel stop. It's really good design to have a peel stop. But if you didn't have that and you had ballast and it scrubbed back like the picture I showed earlier, then that membrane is going to bellow up. Or if your first row of fasteners is 3, 4, 5 feet away, it's going to bellow up and try to pull loose. So we're just testing that to make sure it resists that load. The test is you take a 3-foot long sample, you put a piece of membrane in there, you pull it at a 25-degree angle to failure. So you're pulling it up to just see, how much load it can resist. RE2 is testing the ability of that fascia or gravel stop to stay on the building. And what we're doing is taking a full-size sample. If you make 10-foot piece, it'll be 10 foot, 12 foot, whatever you're making. We're going to attach connection points down the face of it, down the center, and we're going to pull a load on that. And we're going to pull load and hold it, and then relax it. And then we're going to increase load and just keep cycling it up till you have failure. Either it disengages off a cleat, fastener pulls off, something fails, gets so bent that it's no longer functioning as a edge metal. You'll stop the test and you'll record the last load that held that, and then that's what that system's rated for. So again, that calculation we just did, we need to be testing this to 100 pounds or greater. It's got to be greater than 100 pounds per square foot to use that design in the corner. It's just a picture of a fascia being tested. Different ways, different apparatuses that can do it, but they generally all do the same thing, attaching with some kind of a connection, an eye bolt or something to the face of the fascia. We're not pulling on the cleat, we're pulling on the face, the part that's exposed to the wind, the negative pressure. And right now it's under load. You can see that's been out quite a bit. That fascia would have been flat when it started, but when they relax it, it'll go back, and unless it falls off, you're just going to pull it again. Again, you're going to cycle it up till you get failure. Coping, because it's a more 3-dimensional product, it has 2 loads at the same time. And so we tested that. We're going to use a full-size piece of coping, and you're going to put a load down the center of the top and the center of the face, and you're going to load those up and relax them and keep increasing load and cycling that again till failure and record the last load that held that. And then you're going to put an identical sample of coping on the test bed, and you're going to load it on the top and the back at the same time. Cycle that up to failure, record the lowest. And out of those 2 load cases, whichever one has the lowest is what that system is rated at. And again, so for the example we just gave, we're looking at 171 pounds pulling up at the top while you're pulling 100 pounds out on the face. Or you got to be greater than that to meet the loads we just talked about. Here's a picture of a coping being tested. Pulling up on the top. On the left side is the face that's being pulled out at this time. You can't see it as well, but the chains there you can see are pulling out on that face. And again, we're just trying to simulate that negative pressure. Wanted to kind of, I touched on this earlier about putting fascia on a parapet wall. Prior to, in International Building Code 2018 and earlier versions, there was a section of code that said parapet walls should be coated with non-combustible waterproof materials of a width no less than the thickness of the parapet, which I think was probably rightfully so interpreted as you had to do something like in these pictures. You had a metal coping, tile, stone, whatever, something that's non-combustible, put on the top of it. You couldn't wrap the membrane over the parapet and leave it exposed. Spry and others thought, well, there's some good reasons for doing that. We really have to have non-combustible on all our parapets. And in 2021, they changed code to allow that. don't need to read all this code. You can read it if you want to. But basically what it says is you have two types of parapet walls. Some are fire resistant rated. They need to have that non-combustible. That would be an intermediate firewall, or it could be your exterior wall if you're close to another building. If you're too close, you're going to have a fire rated wall. But most parapets don't need that. And so they said when it's not a fire rated wall, or it doesn't need to be fire resistant rated, you just need to be covered with waterproof material, or excuse me, weatherproof material of a width not less than the thickness of the parapet. So you could do a detail like this, where you could wrap that membrane, whatever kind of single ply membrane you're using, up over the wall and just put a fascia on it. A lot of advantages of this to consider. So if from the ground, looking up at a fascia or coping, they look identical. Now, if you have maybe a plaza deck or something out there, maybe you want to put a coping on it to make it look nicer from the backside and from the roof side, or maybe it's windows that look out on it. You just think that a coping is more attractive than membrane. That would make sense. But for functionality, there's a lot of advantages of fascia. It's lower cost per linear foot than coping. You don't need to worry about field measuring the width of that parapet. When you make coping, you got to make it to the size of the parapet. If that parapet width varies, which they frequently do, you got to accommodate that with a coping, but you don't need with a fascia because it's always at the face. It's quicker and easier to install, and you're typically going to get better wind resistance with a fascia system than you will with a coping. You just have that one smaller face to resist the wind, or that the wind load's applied to, as opposed to a coping that has that whole top of the coping. I want to talk quickly about warranties. Warranties are great. If you want a warranty, if your manufacturer or whoever's fabricating the products can give you a warranty, that's good. But it may not be performance based. I would hope that anybody making edge metal is not going to warrant something for greater than what they've tested it for, but they could. Code requires that edge metal be tested. So even if you have a warranty, the manufacturer says, oh, it's warranted to 75 miles an hour, that's great, but you want to make sure that it's tested to resist those loads. It also needs to be installed as tested. So to be ES1 compliant, say this metal's ES1 tested, you got to install it the same way you tested it. You don't have to test every size and every gauge of metal, but you have to you take a design that's been tested, and any product that you make that's that same design, same cleat system, that the cover is no lighter in gauge and no bigger in size than what you tested, has that same rating. So maybe you're going to test a 16-inch coping and 04 aluminum. As long as you make it a 14-inch or smaller than the 16, or you make it a heavier gauge, you make it 050 or something, it still has the same rating. It's going to be strong. The fasteners need to be in the same location, and I think that's critical. I'm a big proponent of pre-drilling, pre-punching holes for those fastener locations when you fabricate it, so that when it's being installed, the person installing it puts the fasteners in the right spot. It's not just the spacing. Frequently you'll see a fastener spaced at 6 inches or 12 inches on center. Nobody's measuring that in the field. So let's just do that for them in the fabrication process. Put those holes in there. And the distance that fastener is from the bottom of the cleat can make a difference too. So it's not just the horizontal distance, but it's also the vertical distance. You want to get them in the right spot. And of course, you want to use the same fastener as you did when you tested it. If you tested it installed with screws, you definitely don't want to put in nails. If you test it with ring shank nails, you don't want to use smooth nails. You certainly need to have that same pull-out resistance and pull-over resistance of the system that had it tested. Okay, I've said before is accept gutters. Well, gutters can also fail in higher winds. And when SPY wrote the first ES1 standard, I think they were looking at what are we seeing failing most? It was coping and fascia. And they said, soon after they realized, what, gutters are failing too. And when gutters fail, frequently we lose the roof. So this is also a code requirement. It went into International Building Code in 2021. It does talk about gutter securement for low slope roofs. And so it says gutters that are used to secure the roof. So that may be a little bit gray. We're trying to clean that up. When I say we, SPRY's trying to clean that up a little bit to get that language more clear as to what we mean by that. My thought, because I've been on a lot of these investigations, when the gutter fails, even if it's not securing the roof, it will typically lead to a roof failure because it's going to take the drip edge or whatever is at the edge of your roof with it. So I really recommend, whether code requires it or not, that all gutters be tested. I'm going to go through this fairly quickly because it's very similar to ES1 testing. Um, like I said, it's been required since 2021. Okay, do I need to do something to get rid of this poll?
You could just click the X on it.
That's what I tried, didn't go away. There we go. Thank you.
Yeah.
Got it. I could answer my own poll. So gutter's been tested since 2021. It's been a code requirement they be tested. Similar test to the ES1. Back. There we go. So the first test G1. This is pulling on the face of the coping, very similar to how we're testing our copings and, excuse me, fascia of the gutter. Very similar to how we're testing coping and fascia. We're putting a load down the center. We're cycling up to failure using a full-size SAM. And here's a gutter being tested. In this presentation, I have a couple different test machines. They're all doing the same thing. They're just applying a load, have some way to measure that load, a load cell or some kind of gauge on it to tell what load you're pulling. The test apparatus can test coping, can test fascia, can test gutter. They all kind of do the same thing. And then we're also testing pulling up on the bottom of the gutter. That's a simulating negative pressure from above, but with the gutter, you're actually getting some positive pressure from below too. That wind coming up the building hits that bottom of it and trying to push it up. And that's what gutters typically do when they fail. They aren't secured well enough at the bottom. In this diagram, that light gray is like a bracket that would help hold it in, but it's not frequently that's not there, or there's nothing to hold it in there, and that gutter will rotate back. And when it rotates back, it flies up on the roof, does damage, and again, maybe causes the roof to fail. These two tests, the G1 and the G2, are what are required by the 2021 version of International Building Code. We're testing the wind loads on gutter. This is what the G2 looks like. We're pulling up on the bottom. That gutter's pretty deformed, but it will spring back when that load's taken off of it, and still they'll keep going until something fails. And this third test is not a code requirement, but it's a pretty good test. What we're testing for here is if that gutter, the downspout should clog and it fills full of water, or if you're in an area where you get a snow and ice load, it's going to be trying to pull that gutter off the building. That's not in the current version of code. It's proposed to change in the next version of code. But again, might be a good test if you're doing gutters to make sure that it doesn't fall off the building if it gets too much weight on it. It looks like that. Again, we're doing this just a different machine pulling the same kind of loads. This is not about low slope. I just got to hit this real quick. Metal Construction Association is metal roofing, and they found that like low slope, found that edge metal is where single ply roofs were failing. Metal Construction Association found that metal roofs, when they fail, were probably because the flashings failed. And so they patterned test standards that's very much patterned after the ES1 test standard. And so for those of you that are doing metal roofing, steep slope metal roofing, there might be some, it's not a code requirement yet. I know they're trying to get this into code. Might be something to consider. There's different tests. They can test eave trim pulling out. It's very similar to an ES1 test. When you do like a gable trim like this, it has two surfaces. They're testing like coping, pulling it in two directions. And for hip and ridge, again, you're pulling it in two directions. I can wrap up with kind of some other considerations for metal in general and like I said, perimeter edge metal in specific, metal thicknesses, galvanic reaction, substrate, what are we attaching to, and ancillary components. These are things that could be attached to your edge metal system. So metal thickness, everybody thinks, okay, let's make it thicker or make it stronger. And that's typically true. And as I told you before, that's the way it's interpreted. If you test a low gauge, go heavier gauge. But that's not all there is to it. There's a lot of factors for how something performs. So I highly recommend doing some testing to make sure that really heavier gauge is going to perform better. Thicker metal is typically thought of, let's use thicker metal to prevent oil canning. It will greatly reduce oil canning. I do recommend going to heavier gauge if you're concerned about that. But again, that's not the only factor, and I'll talk about that in a second too. But obviously the material thickness is important. Kind of a good rule of thumb, design an edge metal, you're going to have cleats that are at least 1 gauge heavier than your cover. That's, there's kind of some rules like that that you might want to consider. SMAC has some good design on how to do edge metal, but SMAC is kind of just how to make it. using testing to make sure it still performs. Thermal expansion is something you certainly need to design for. Metal expands when it heats and contracts when it cools. I think most people know that. It's not just that it expands and contracts, it typically expands and contracts at a different rate than what's attached to. So you're attaching your edge metal to a building that's masonry or wood or something like that, that's not going to move near as much as the metal. You need to allow for that metal to expand and contract and move freely while you put it on a cleat frequently, or if you're not on a cleat, really should have a slotted or oversized hole to allow it to move uh, uh, with the fasteners and not be pinned between fasteners. And then where the most common issue you need to worry about expansion, contraction, and edge metal is at the joints. In this picture, this was a gravel stop. It's on a cleat, but it was butted dead tight when they installed it on a cool day. When it heated up, that metal expanded, and those two ends had just pushed into each other, and it literally pushed them off the cleat. That's what you can kind of see here where this is pushed away. So it's now disengaging from the cleat. Wind will catch that and blow it off. So you want at your joints to leave some way for expand and contract. One way you can do is to lap it and just let them slide back and forth across each other. That works fine. With thicker metal, it may not be attractive because you get that edge metal there. And over time, you can get some rub that might wear your paint, but it works. The other option is to just leave a small gap, an 1/8 or 1/4 inch gap, and use a splice plate. It could be an external splice plate, or it can be an internal. I personally like internal. I think it's a little cleaner looking, but they both do the function. They cover up that joint, either front of it or back of it, and allow the metal to expand and contract. Oil canning, as I touched on before, nobody likes the looks of oil canning, all this waviness. You put up metal, you want it to stay nice and flat. Going heavier gauge will certainly help reduce oil canning. In this picture, you can see those roof panels have pencil ribbing in it. That helps to reduce oil canning, but it clearly did not do the case in this. What causes oil canning is stress on the metal. Most commonly, I see that as thermal stress, metal expanding, contracting due to heat. It could be done in the fabrication process. If you don't have your roll former set up right, or you're using bad metal, it may be wavy. And then that's just because you built some stress into it when you made it. But if you have a coping or roof panel that's laying on the ground and it looks beautiful and it's flat, and you install it, and a couple days later you go out there and it looks like this, it's because it's expanded and you've not allowed for that. It's been pinned. So I can look at these pictures even, and you can kind of tell where the clips are too tight, not allowing this metal to move. And so the metal expands in between the attachment points and bellows up and causes oil canning. So it's really important to allow for that thermal movement with clips, cleats, slotted holes, or oversized holes to allow the metal to move around the fasteners. Galvanic compatibility is dissimilar metals. You don't have metals that are very different from each other on the galvanic reaction chart in contact with each other. This is a pretty simplified version of a galvanic reaction chart where you got magnesium on the left, gold on the right, and things in between. You could put in all the metals in there. Where that metal is on the chart isn't important. It's that if you have two metals that are far apart from each other on the chart in contact, you're going to get corrosion. And you're going to get corrosion on this chart on those on the left side. So in this picture, we've got a copper counter flashing going over an aluminum flashing. The copper's got some discoloration on. That's just normal patine on the copper. The aluminum, if you can see, is getting very corroded away. That white rust, aluminum oxide, it's rusting away because of the corrosion, because it's in contact with the copper. So you can see on this chart, aluminum is right far to the left of copper. You don't want to do that. It's the aluminum that's corroding away. This is just like a year or two old, and you're already having that kind of corrosion. Like to point out that zinc and aluminum are right next to each other on that chart. That's commonly what you're seeing with edge metal. It's going to be galvanized steel, which is zinc coated steel, or aluminum. So you can use a galvanized cleat with aluminum. It works really well. And the zinc is actually there to protect the steel. So if you get any corrosion, it's the zinc going away, not your steel and not your aluminum. Again, you can use other metals. You just want to make sure that they're close together on this chart. Substrates are what are we attaching to? So I see edge metal failures, and frequently if it's not some problem with the way the edge metal was made and installed, it's actually the nailer, the thing it attached to failed, or that it wasn't attached well. So your substrate is what you're attaching to. Most commonly it's wood, and almost everybody I know that's doing testing is doing it into wood. But you can install into masonry or steel or some other substrate. You just want to make sure you have fasteners that have the same pull-out resistance as they do in wood. Pretty easy to do. If you use nails going into wood, you can use screws going into masonry or into steel. You want to make sure that that wood blocking is secure. This is a common problem you see is something like this where the wood blocking came loose. Factory Mutual has a data sheet 149 that is a pretty good document to go see, how do you attach that wood blocking? What should be the spacing of your fasteners? SPRY has a document too. It's not a code requirement, but it's SPRY ED1. You can go to their website and look at that. All the SPRY standards I talked about are free on their website as well. So the picture on the left, I think, is interesting because you see the magnitude of that load. When that membrane got billowed up, it pulled not only the edge metal still attached to the wood here, by the way. It pulled the wood blocking and the first course of concrete up with it. Shows the force of what we're trying to resist. By the way, when you embed into masonry units like this, FM 149 says you should go down 2 courses. That's why that top course came off. Now, I don't know, maybe it would have taken 2 courses or been down further, but it would have been better if they'd gone down to the second course. Picture on the right you see is a nail that's into the masonry. The nail held really well. It did not pull out. That's a common problem. This nail was pulling out. The nail didn't pull out, but it's such a small head, the wood just pulled right through it. And now you had a hole in your piece of wood. In the middle, we've got a bolt that's a little bit bigger head than a nail, but ideally that should still have a washer. Again, I don't know, it might have broken loose and failed anyway, but you need a washer on that. And the other common thing is pull out of fasteners. I see that more often in re-roofing where they've had like one layer of blocking and they put on more insulation. They add on another layer of blocking. The second one is not adequately secured to the first. So you need to, not just nail it off, but get it screwed down and make sure it can resist the loads. Wrap it up here with ancillary components. So what do we attach to it? Most common, this is lightning protection. Could be signage, could be lighting or something like that. But the basic thing is don't attach stuff to your edge metal system. They're designed to resist that negative pressure wind load. They're not designed typically to withstand a lightning protection that becomes a sail up there moving around. Cabling can limit the thermal expansion and contraction, add extra weight to it, can be a problem. The picture on the right, I think is a really elegant solution. There's nothing proprietary. Anybody could make this. It's just a bracket that goes on the coping, on the parapet wall underneath the coping. It keeps the lightning protection off of the coping and also keeps lightning protection off of the membrane that's wrapping that wall. It's the waterproofing. The membrane manufacturer doesn't want holes going through his membrane either. Bracket just looks like this. Pretty simple little bracket. I've seen them made out of aluminum and stainless steel. And you attach them to the wall. And then the other beauty of that is it allows either the lightning protection installer or the coping installer to come in independently of each other. Bracket goes up first. Lightning protection is ready to go. We can put it up. Coping guys ready to go and put it up at any time. If you go to re-roof, you don't have to worry about that coordination of those subs. And this is, again, I don't need to read this long code language, but this was a code that went in 2024 of International Building Code, pretty much saying that for lightning protection people, this is really addressing them because it talks about how to install lightning protection in general for safety of, so that it functions for lightning strikes, but it didn't address what impact it could have on the edge metal. So they put this in code just saying, if you are installing lightning protection on ES1 tested metal, consult the manufacturer of that product or get a design professional involved to make sure you do it right. So edge metal failure is leading cause of roof failures. Tested per ANSI SPRY FM 4435 ES1 is a code requirement, has been for quite a while. And then a newer version, 2021, starting to be a few years ago now, of code requires that gutters also be tested. And I always like to say, codes are your minimum design requirements. You can specify heavier, you can specify warranties, you can specify more, but at minimum, meet code. And that is all I've got. And I'm happy to take questions. I think we got about 6 minutes left. If however much we've got, I can answer those, Kayla.
Perfect. Sounds good. All right, let's pull up the questions here. All right. Cool. All right. So, first question. This person says, They think they missed maybe this part in the beginning, but did you mention if you supply metals for high slope asphalt shingle roofs or only commercial low slope?
Mike, ATAS can do that. Yeah, this is what I'm really talking about here is just low slope. It's not tested, but yeah, we can we're a big job shop and we do a lot more than that. But yeah, we can certainly do edge metal for steep slope stuff too. But it's typically we're going to work in compared to that industry, heavier gauges, 24 gauge steel, 040, 032 aluminum, not super light 0.19, something like that, which maybe a residential guy would use. That would not be us.
Okay, gotcha. All right, next question. Um, are there standard edge metal details available to resist specific pull loads, for example, 80 PSF?
Oh, 80 PSF. So again, the edge metal has to be tested, and you're testing to resist a load. You can't just go copy a detail and say that works. It is a tested system. So you're really testing what that manufacturer makes. So ATAS made products and we sent it to labs and had it tested. There are some programs you can use. NRCA has one where they tested some edge metal, and as a contractor, you can sign up for their program. You pay a fee, and then they send you the fabrication details, and they come and audit your facility and make sure that you have the capability of making the same product that they tested. So it's a little bit different way of doing it, sublisting, but they're going to want to make sure you can make it. You can look up the NRC details, and I can look at that and I say, okay, there's a lot of different ways I can make that same shape, and it won't perform exactly the same. So when you sign up for those programs, they're not going to just tell you what the end product looks like. They're going to give you the fabrication details. Here's how you make all the parts. So there's a way you can get that done, but you can't just go. I can't give you a product and say, yeah, go make that. It's going to resist 80 pounds. Somebody has to have tested it to prove that.
Hmm. Wonderful. All right. I have somebody asking for the presentation deck. So just to confirm, is that something you can share, Bob, with
Yeah, we probably can just to get us information on that. You can do that.
some? Yeah, that's great. All right. Next we have, I have seen window washing ropes, safety lines going over parapets. Any reinforcement built to the edges to help with that?
I I have not seen any metal coping systems that can resist that weight load. They should not be doing that. They got to have some way to hold that off of it. No, it's not recommend you do that. You're going to do some damage. You could dislocate the system depending on how it's installed. Yeah, I've seen that too. I mean, if it's just a rope going over it, probably not going to do any damage. But if you have any load on it, that would not be good.
Right. Absolutely. All right. And maybe this is something you can just comment on because it doesn't seem like a question, but many contractors do not understand the electrolytic, and I'm not sure if I'm saying that right,
That's yeah.
corrosion, corrosion from dissimilar metals. They often use incompatible fasteners.
Yeah, that's correct. And I didn't, that's what I was talking about with Galvanic. It's that it's not just the two metals together, like I said, zinc and aluminum, but yeah, fasteners that are not compatible with the metal. And what I didn't touch on, I should have, is that most treated wood blocking is now treated with copper sulfate. That's what they use to make it so it's insect and rot resistant. And so you got to think of that wood blocking as being copper. So you certainly don't want to use aluminum in contact with it, aluminum nail, or even a steel nail. Ideally stainless steel. We supply stainless steel with all our products just to be safe. There are some coated fasteners that work. Galvanized, hot dipped. I wouldn't use electroplated because it can wear off. So yeah, it's a good comment. And that yes, you definitely need to be aware of the fasteners you're using and make sure that they're compatible. I've been on a lot of these recovery investigations. You have the nails just look like what used to be a nail looks about like a needle. It's just rusted away to nothing.
Mm, awesome. Well, thank you for that, Bob. I think that's the
Sure.
last question for now. So, we are
Perfect,
right
because we're
about time.
right at
So,
our time. So
yeah, any final comments you'd like to make?
no, like I said, reach out to us and you can see atest.com's there. My email address is bleclare, BLECLARE at atest.com, or reach out to Kayla and we can help you out with anything you need. And thank you for your time.
Yeah, thank you. Yeah, absolutely. And like I mentioned at the beginning, if you filled out the poll, you'll get an email within the next few days. That is a direct line of communication with Bob and his team. It'll come from a no reply at Acelab email address. So you can respond to that still to respond to the message and ask any specific questions, or like I said, you can log into your Acelab account and begin that conversation there. So thank you, Bob and Jason, and we're glad to have you. And we hope everyone has a great day.
Great. Thank you, Kayla.
Thank you. Bye.